Hey students, let me answer some of the questions you guys have had recently. Let me look down on my laptop and jump over to this view here, teaching view. Yep. First question, what is a sound wave? It might be useful to think of a water wave first. Here's some waves at the beach, right? That's cool. Right here on the right side, let's look at this in detail. So here we have a water wave. Let's say there's an earthquake somewhere out in the ocean, creates this wave that's going out towards the continents, right? This is what's happening. This is not the only way that waves can happen in the ocean, but right. The idea, there are two ideas I want to get across here. Number one is there are peaks and valleys, which they're calling crests and troughs. I'm going to call it peaks and valleys. And the peak is the top of the wave, right? And the valley is the bottom of the wave. And this dotted line right here, what they're calling calm sea level, is what I'm going to call the origin. And the distance from that origin, or that dotted line, where if the water were at rest, the distance from there up to the peak is called the amplitude. They're calling the wave height. I'm going to call it the amplitude when we get the sounds. So here is another Wikipedia article about water and waves. Again, so the amplitude is the distance from that origin or that resting state up to the peak right there, what I'm circling with my cursor right now. And the distance from one crest or one peak to the next is called the frequency in sound waves, the frequency of the sound. And that's measured in how many peaks there are in 1 second. And the higher the number of peaks in 1 second of sound, the higher the pitch will be. Okay. And the larger the amplitude, or the larger the peak is, the louder the sound will be. So to take an example, let's go over to Pratt and let's just create. If I do new, do sound, let's create a pure tone. If I say, hey, I want to do a pure tone, let's make it a second long. Let's do, we'll just do 440 hertz. The tone frequency there, 440 hertz, the Hz is hertz. That's how many peaks there are in 1 second. And we'll leave the amplitude at 0.2 Pascal, which is a measure of amplitude or loudness. Let's just do that. Let's listen to this. Here we go. Listen to this. Okay. Cool. That is A above middle C. If I do a virtual piano, I bet I can get one quickly here. Yeah, that what we just heard is what's called a virtual, or excuse me, that was A above middle C. Middle C. So that's what we heard. Right. Okay, so we're hearing, so the A above middle C on the piano has a frequency of 440 hertz. That is, there are 440 peaks in 1 second during that sound. Let's rename that real quick so we don't get confused on what we just heard. Let's call that A above middle C, and it was at 0.2 Pascal. Let me just write that down too, because we're gonna bump up the amplitude here in a second. Let's create another one real quick. Let's go to sound, create pure tone. This time let's do 261.6 hertz, and we'll keep it at 1 second and 0.2 Pascal. This is middle C. Middle C should be right here. So that's middle C. Middle C has a frequency of 261.6 according to our website. So that's cool. Now let's talk about amplitude a bit more. Let's create those same sounds. Let me rename this real quick before we move on. That was middle C at 0.2 Pascal. Awesome. Let's bump up the amplitude quite a bit. Let's go to sound. Let's do a pure sound. Let's go back to 440. Let's bump this up to, say, 0.5. So we were at 0.2 Pascal. Let's go up to 0.5 Pascal. This should be substantially louder. Here's the previous one. Okay, so let's rename that real quick so we don't get confused on what we're listening to. This is A above middle C at 0.5 Pascal. Okay, good. Let's jump up. Let's just bump it up. Let's go to new sound, pure tone. Let's go back to middle C, which is 261.6. Let's bump this up to something really loud. Let's say 4 Pascal. And we're going to call this, we can rename it right here. This is middle C at 4 Pascal. Ready, set, let's see. Oh, okay, they want underscores. That's fine. I'll put some underscores in there for them. Now listen to this. So that's at 4 Pascal. Has the same frequency, has the same pitch or the same musical note, but much louder because the amplitude is much bigger. And we can look at that. If we just open this up and look, yeah, I mean, it's only 0.2. You can see that says 0.2 right there. This is the middle C at 0.2 Pascal. It says 0.2 right there. If we were to open this up in our window editor, we'll see it's up to 4. I mean, it's measuring it right there. It looks the same. It's taking the same amount of space on my screen, but it's actually much louder. Want to listen again? Yep, versus this. Okay, so that's amplitude and frequency of a sound. That is the number of peaks within a second. That's measured in hertz, named after some person with the last name Hertz. That's simply, again, the number of peaks in a sound wave within a second. And the amplitude is how far from the origin or the resting point it is up to the peak. The bigger the amplitude, the louder the sound. Okay, good. Let's go back to here. We got that, we got those. Good, so that's what a sound wave is. It's simply a wave moving through the air, moving through air molecules and hitting our eardrum, and we're hearing it. We're hearing that the frequency with which our eardrum gets hit, right? It changes the pitch, and the amplitude, how much it's getting hit, changes how loud it is. Okay. Next question, what is the sampling rate I want to answer? Next question I want to answer in this video is, what is the sampling rate? It is a way to digitize a sound. So, a little background. An analog wave sound is a continuous pressure. Well, it's pulsating, but there's a continuous amount of information coming into your eardrum, hitting your eardrum. But we can't ask a computer to take an infinite number of samples of that wave, right? That's not possible for computers to do. So we have to discretize. That is, we have to take a discrete number of samples of that wave, and the number of samples we take is called the sampling rate. It's also referred to as the sample rate, and it's also referred to as the sample frequency. I'm going to try to use sample rate only to not get confused with the frequency of a sound in hertz. That is the number of peaks in a second, which is different from the sampling rate. But you may hear people say sampling frequency, but I'm going to say sample rate. And the higher the number of samples you have in a second of sound, the better the quality, like the better the representation is of the actual sound. Meaning the digital representation of the sound that is discretized, that is discrete samples, n number of samples per second. The more samples you have within a second, the more faithfully that digital sound file will represent the actual sound. Okay, let's take a look at the actual samples in Audacity. So let's go over to teaching mode again. Let's go to Audacity. So in this project, I'm gonna change the sampling rate. The default is 48,000 hertz, but I'm gonna go down to like 1,000. Just go down to 1,000 hertz per second. Or excuse me, 1,000 samples per second. I may interchange those. Hertz is something per second. In this case, it's samples per second. Good, so if I just record this, I'm just gonna record something simple. Ready, set, testing, 1, 2, 3. Okay, let's go ahead and bump this up. Let's amplify it so we can make sure it's loud enough for us to hear. Good, listen to this, ready? What? I can't understand anything. That did not sound like what I said at all, right? So let's zoom in a bit. Let's zoom in to somewhere in here. Let's look at 100 milliseconds right in here. We're going from 1.2 seconds to 1.3 seconds. That's 100 milliseconds. There should be 100 little dots in here. There should be 100 samples in here. Let's actually zoom in here. Let's go from 1.25 to 1.26, which would be 10 milliseconds, right? And we should have 10 dots in here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 samples in 10 milliseconds. There's one sample per second. And as we heard, it does not sound good at all. Let's listen to it again. Like, it's not representing what I said at all. So a sampling rate of 1,000 is just horrible. Okay. Let's create a new project, and let's change the sampling rate up to, let's try 2,000. Change the project sampling rate. Let's go to other, and let's do 2,000 hertz, 2,000 sampling rate. Good. And let's try it again. Testing 4, 5, 6. Let me just go ahead and bump this up real quick. Amplify it to make sure it's loud enough for us. Listen. Again. Okay, I'm getting it a little bit. I'm getting testing 4, 5, 6. It's super high pitched. That doesn't sound like me. Let's zoom in a bit here. Let's do what we did before. Let's kind of zoom in. Let's zoom into about there. Let's go from 1.17 to 1.8. This would be 10 milliseconds. Let's see how many samples we have here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Yep, there are 20 in a 10 millisecond because we had a sampling rate of 2,000 hertz per second. Now, if you were to connect the dots, if you were to connect this dot to that dot, to that dot, to that dot, to that dot, etc., you're beginning to see a wave, right? We're seeing the beginnings of a wave there. Okay, cool. Let's try it again. Let's bump it up to, let's jump up to 4,000 this time. Let's go up to 4,000 hertz. 4,000 there. I'll do the same thing. Testing 6, 7, 8. I forgot what numbers I was on. Let's bump that up real quick. Effect, amplify. Good. Let's listen to it. Ready?
Testing 6, 7, 8.
Okay, that's sounding more.
Testing 6, 7, 8.
That's sounding better, right? Let's zoom in on that. Let's just go into, I don't know where we should go. Just go in anywhere in here. Let's find a 10 millisecond span right in about there. So we should have 40, if I'm not mistaken. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I'm assuming there's 40 in there. I'm about halfway across and I have 20. So anyway, the number of samples here has gone up, right? So we have 40 samples for a 10 millisecond window. And so that, if you connect those dots on each of those samples and it's looking more and more like a wave, right, a sound wave, let's just go ahead and bump it up. Let's do one more time. Let's just go, let's try maybe 8,000 hertz. 8,000 hertz here. And here we go. Testing 9, 10, 11. Okay. Let's just bump up the volume real quick, amplify it to the loudest it can go, and we'll take a look. Let's just zoom into about there. What is this? Let's go from here to look at a 10 millisecond. And here we should have 80. Is that, let's see real quick. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We should have 80 in here, if I'm not mistaken. Am I doing that math correctly? Pretty sure that there should be 80 samples in here. And if you connect all those dots, those discrete points, right? Those are discrete points there. Then you end up with, you know, a wave that is looking more and more like the actual wave that hit this microphone's diaphragm. But let's just do one more. Well, let's just back up to here. Let's listen to it all.
Testing 9, 10, 11.
Okay, that sounds better. Let's bump it up to, let's go all the way up to the CD quality of 44,100 hertz. Here we go. Testing 15, 16, 17. And let's just let's do real quick, amplify that for good measure. Let's look at it, listen to it. Testing 15, 16, 17. Right, so that sounds really good. Sounds basically like what you would hear if you're standing next to me and I spoke directly into your ear, not through a microphone that's doing a digital sampling with discrete samples.